In mathematics, in set theory, the constructible universe, denoted all, is a particular class of sets that can be described entirely in terms of simpler sets. It was introduced by Kurt Gödel in his 1938 paper, The Consistency of the Axiom of Choice and of the Generalized Continuum-Hypothesis. In this, he proved that the constructible universe is an inner model of ZF set theory, and also that the axiom of choice and the generalized continuum hypothesis are true in the constructible universe. This shows that both propositions are consistent with the basic axioms of set theory, if ZF itself is consistent. Since many other theorems only hold in systems in which one or both of the propositions is true, the consistency is an important result. What is L? L can be thought of as being built-in stages, resembling the von Neumann universe. The stages are indexed by ordinals. In von Neumann's universe, at a successor stage, one takes V alpha plus 1 to be the set of all subsets of the previous stage, V alpha. By contrast, in Gödel's constructible universe L, one uses only those subsets of the previous stage that are definable by a formula in the formal language of set theory, with parameters from the previous stage and with the quantifiers interpreted to range over the previous stage. By limiting oneself to sets defined only in terms of what has already been constructed, one ensures that the resulting sets will be constructed in a way that is independent of the peculiarities of the surrounding model of set theory and contained in any such model. Define L is defined by transfinite recursion as follows. If is a limit ordinal, then here alpha less than lambda means alpha precedes lambda. Here or denotes the class of all ordinals. If Z is an element of L alpha, then Z equals Y, YL alpha and YZ def equals L alpha plus 1. So L alpha is a subset of L alpha plus 1, which is a subset of the power set of L alpha. Consequently, this is a tower of nested transitive sets. But L itself is a proper class. The elements of L are called constructible sets, and L itself is the constructible universe. The axiom of constructibility, aka V equals L, says that every set is constructible, i.e., in L. Additional facts about the sets L alpha. An equivalent definition for L alpha is, for any ordinal alpha, for any finite ordinal n, the sets Lane and Vn are the same, and thus L omega equals V omega. Their elements are exactly the hereditarily finite sets. Equality beyond this point does not hold. Even in models of ZFC in which V equals L, L omega plus 1 is a proper subset of V omega plus 1, and thereafter L alpha plus 1 is a proper subset of the power set of L alpha for all alpha greater than omega. On the other hand, V equals L does imply that V alpha equals L alpha if alpha equals omega alpha, for example if alpha is inaccessible. More generally, V equals L implies H alpha equals L alpha for all infinite cardinals alpha. If alpha is an infinite ordinal, then there is a bijection between L alpha and alpha, and the bijection is constructible. So these sets are equinumerous in any model of set theory that includes them. As defined above, def is the set of subsets of X defined by delta zero formulas that use as parameters only X and its elements. An alternate definition, due to Gödel, characterizes each L alpha plus 1 as the intersection of the power set of L alpha with the closure of under a collection of 9 explicit functions. This definition makes no reference to definability. All arithmetical subsets of omega and relations on omega belong to L omega plus 1. Conversely, any subset of omega belonging to L omega plus 1 is arithmetical. On the other hand, L omega plus 2 already contains certain non-arithmetical subsets of omega, such as the set of true arithmetical statements. All hyperarithmetical subsets of omega and relations on omega belong to, and conversely any subset of omega that belongs to is hyperarithmetical. L is a standard inner model of ZFC. L is a standard model, i.e., it is a transitive class and it uses the real element relationship, so it is well-founded. L is an inner model, i.e., it contains all the ordinal numbers of V and it has no extra sets beyond those in V, but it might be a proper subclass of V. L is a model of ZFC, which means that it satisfies the following axioms. Axiom of regularity. Every non-empty set X contains some element Y such that X and Y are disjoint sets, is a substructure of which is well-founded, so L is well-founded. In particular, if XL, then by the transitivity of L, YL. If we use this same Y as in V, then it is still disjoint from X because we are using the same element relation and no new sets were added. Axiom of extensionality. Two sets are the same if and only if they have the same elements. If X and Y are in L and they have the same elements in L, then by L's transitivity, they have the same elements, so they are equal. Axiom of empty set. Is a set equals L0 equals Y, YL0 and Y equals Y, L1. So L, since the element relation is the same and no new elements were added, this is the empty set of L. Axiom of pairing. If X, Y are sets, then X, Y is a set. If XL and YL, then there is some ordinal alpha such that XL alpha and YL alpha. Then, X, Y equals S, SL alpha and L alpha plus 1. Thus, X, Y, L and it has the same meaning for L as for V. Axiom of union. For any set X there is a set Y whose elements are precisely the elements of the elements of X. If XL alpha, then its elements are in L alpha and their elements are also in L alpha. So Y is a subset of L alpha. Y equals S, SL alpha and there exists ZX such that SZ, L alpha plus 1. Thus YL. Axiom of infinity. There exists a set X such that is in X and whenever Y is in X, so is the union YU, Y. From transfinite induction, we get that each ordinal alpha L alpha plus 1, in particular, omega L omega plus 1 and thus omega L. Axiom of separation. Given any set S and any proposition P, X, XS and P, is a set. By induction on subformulas of P, one can show that there is an alpha such that L alpha contains S and Z1, Zinken. So, X, XS and P holds in L equals X, XL alpha and XS and P holds in L alpha plus 1. Thus the subset is in L. Axiom of replacement. Given any set S and any mapping where P and P implies Y equals Z, Y, there exists XS such that P is a set. Let Q be the formula that relativizes P to L, i.e., all quantifiers in P are restricted to L. Q is a much more complex formula than P, but it is still a finite formula, and since P was a mapping over L, Q must be a mapping over V, thus we can apply replacement in V to Q. So, Y, YL and there exists XS such that P holds in L equals Y, there exists XS such that Q is a set in V and a subclass of L. Again using the axiom of replacement in V, we can show that there must be an alpha such that this set is a subset of L alpha plus 1. Then one can use the axiom of separation in L to finish showing that it is an element of L. Axiom of power set. For any set X there exists a set Y, such that the elements of Y are precisely the subsets of X. In general, some subsets of a set in L will not be in L, so the whole power set of a set in L will usually not be in L. What we need here is to show that the intersection of the power set with L is in L. Use replacement in V to show that there is an alpha such that the intersection is a subset of L alpha. Then the intersection is Z, ZL alpha and Z is a subset of X, L alpha plus 1. Thus the required set is in L. Axiom of choice. Given a set X of mutually disjoint non-empty sets, there is a set Y containing exactly one element from each member of X. One can show that there is a definable well-ordering of L which definition works the same way in L itself. So one chooses the least element of each member of X to form Y using the axioms of union and separation in L. Notice that the proof that L is a model of ZFC only requires that V be a model of ZF, i.e., we do not assume that the axiom of choice holds in V. L is absolute and minimal. If W is any standard model of ZF sharing the same ordinals as V, then the L defined in W is the same as the L defined in V. In particular, L alpha is the same in W and V for any ordinal alpha, and the same formulas and parameters in Def produce the same constructible sets in L alpha plus 1. Furthermore, since L is a subclass of V and, similarly, L is a subclass of W, L is the smallest class containing all the ordinals that is a standard model of ZF. Indeed, L is the intersection of all such classes. If there is a set W in V that is a standard model of ZF, and the ordinal kappa is the set of ordinals that occur in W, then L kappa is the L of W. If there is a set that is a standard model of ZF, then the smallest such set is such a L kappa. This set is called the minimal model of ZFC. Using the downward-Lowenheim-Skolem theorem, one can show that the minimal model is a countable set. Of course, any consistent theory must have a model, so even within the minimal model of set theory there are sets that are models of ZF. However, those set models are non-standard. In particular, they do not use the normal element relation and they are not well-founded. Because both the L of L and the V of L are the real L and both the L of L kappa and the V of L kappa are the real L kappa, we get that V equals L is true in L and in any L kappa that is a model of ZF. However, V equals L does not hold in any other standard model of ZF. L and large cardinals since on LV. Properties of ordinals that depend on the absence of a function or other structure are preserved when going down from V to L. Hence initial ordinals of cardinals remain initial in L. Regular ordinals remain regular in L. Weak limit cardinals become strong limit cardinals in L because the generalized continuum hypothesis holds in L. Weakly inaccessible cardinals become strongly inaccessible. Weakly Marlow cardinals become strongly Marlow. And more generally, any large cardinal property weaker than 0 hash will be retained in L. However, 0 hash is false in L even if true in V. So all the large cardinals whose existence implies 0 hash cease to have those large cardinal properties, but retain the properties weaker than 0 hash which they also possess. For example, measurable cardinals cease to be measurable but remain Marlow in L. Interestingly, if 0 hash holds in V, then there is a closed unbounded class of ordinals that are indiscernible in L. While some of these are not even initial ordinals in V, they have all the large cardinal properties weaker than 0 hash in L. Furthermore, any strictly increasing class function from the class of indiscernibles to itself can be extended in a unique way to an elementary embedding of L into L. This gives L a nice structure of repeating segments. L can be well ordered. There are various ways of well ordering L. Some of these involve the fine structure of L, which was first described by Ronald Bjorn Jensen in his 1972 paper entitled The Fine Structure of the Constructible Hierarchy. Instead of explaining the fine structure, we will give an outline of how L could be well ordered using only the definition given above. Suppose X and Y are two different sets in L and we wish to determine whether X less than Y or X greater than Y. If X first appears in L alpha plus 1 and Y first appears in L beta plus 1 and beta is different from alpha, then let X less than Y if and only if alpha less than beta. Henceforth, we suppose that beta equals alpha. Remember that L alpha plus 1 equals def, which uses formulas with parameters from L alpha to define the sets X and Y. If one discounts the parameters, the formulas can be given a standard Gödel numbering by the natural numbers. If phi is the formula with the smallest Gödel number that can be used to define X, and psi is the formula with the smallest Gödel number that can be used to define Y, and psi is different from phi, then let X less than Y if and only if phi less than psi in the Gödel numbering. Henceforth, we suppose that psi equals phi. Suppose that phi uses n parameters from L alpha. Suppose Z1, zinc is the sequence of parameters that can be used with phi to define x, and W1, Wn is the same for y. Then let x less than y if and only if either zinc less than Wn or etc. This is called the reverse lexicographic ordering. If there are multiple sequences of parameters that define one of the sets, we choose the least one under this ordering, it being understood that each parameter's possible values are ordered according to the restriction of the ordering of L to L alpha. So this definition involves transfinite recursion on alpha. The well-ordering of the values of single parameters is provided by the inductive hypothesis of the transfinite induction. The values of n tuples of parameters are well-ordered by the product ordering. The formulas with parameters are well-ordered by the ordered sum of well-orderings, and L is well-ordered by the ordered sum of the orderings on L alpha plus 1. Notice that this well-ordering can be defined within L itself by a formula of set theory with no parameters, only the free variables x and y. And this formula gives the same truth value regardless of whether it is evaluated in L, V, or W, and we will suppose that the formula is false if either x or y is not in L. It is well known that the axiom of choice is equivalent to the ability to well-order every set. Being able to well-order the proper class 5 is equivalent to the axiom of global choice, which is more powerful than the ordinary axiom of choice because it also covers proper classes of non-empty sets. L has a reflection principle, proving that the axiom of separation, axiom of replacement, and axiom of choice hold in L requires the use of a reflection principle for L. Here we describe such a principle. By mathematical induction on n less than omega, we can use ZF in V to prove that for any ordinal alpha, there is an ordinal beta greater than alpha such that for any sentence P with Z1, Zk in L beta and containing fewer than n symbols we get that P holds in L beta if and only if it holds in L. The generalized continuum hypothesis holds in L. Let T be any constructible subset of S. Then there is some beta with so for some formula phi and some drawn from by the downward Lowenheim-Skolem theorem, there must be some transitive set K containing and some, and having the same first-order theory as with the substituted for the, and this K will have the same cardinal as, since is true in, it is also true in K, so for some gamma having the same cardinal as alpha, and because and have the same theory, so T is in fact in. So all the constructible subsets of an infinite set S have ranks with the same cardinal kappa as the rank of S. It follows that if alpha is the initial ordinal for kappa plus, then serves as the power set of S within L, and this in turn means that the power set of S has cardinal at most alpha. Assuming S itself has cardinal kappa, the power set must then have cardinal exactly kappa plus. But this is precisely the generalized continuum hypothesis relativized to L. Constructible sets are definable from the ordinals. There is a formula of set theory that expresses the idea that x equals L alpha. It has only free variables for x and alpha. Using this we can expand the definition of each constructible set. If S L alpha plus 1, then S equals y, L alpha and phi holds in, for some formula phi and sim Z1, zinc in L alpha. This is equivalent to saying that, for all S if and only if there exists x such that x equals L alpha and y x and psi, where psi is the result of restricting each quantifier in phi to x. Notice that each ZKL beta plus 1 for some beta less than alpha. Combine formulas for the z's with the formula for s and apply existential quantifiers over the z's outside and one gets a formula that defines the constructible set S using only the ordinals alpha that appear in expressions like x equals L alpha as parameters. Example: the set 5 omega is constructible. It is the unique set S that satisfies the formula, whereas short for. Actually, even this complex formula has been simplified from what the instructions given in the first paragraph would yield. But the point remains. There is a formula of set theory that is true only for the desired constructible set S, and that contains parameters only for ordinals. Relative constructibility. This gives rise to the concept of relative constructibility, of which there are two flavors, denoted L and L. A. The class L for a non-constructible set A is the intersection of all classes that are standard models of set theory and contain A and all the ordinals. L is defined by transfinite recursion as follows. L0 equals the smallest transitive set containing A as an element, i.e., the transitive closure of A. L alpha plus 1 equals def. If lambda is a limit ordinal, then, if L contains a well-ordering of the transitive closure of A, then this can be extended to a well-ordering of L. Otherwise, the axiom of choice will fail in L. A common example is L, the smallest model that contains all the real numbers, which is used extensively in modern descriptive set theory. The class L, A, is the class of sets whose construction is influenced by A, where A may be a set or a proper class. The definition of this class uses defer, which is the same as def except instead of evaluating the truth of formulas phi in the model, one uses the model where A is a unary predicate. The intended interpretation of A is YA. Then the definition of L, A, is exactly that of L only with def replaced by defer. L, A, is always a model of the axiom of choice. Even if A is a set, A is not necessarily itself a member of L, A, although it always is if A is a set of ordinals. It is essential to remember that the sets in L or L, A, are usually not actually constructible, and that the properties of these models may be quite different from the properties of L itself.